We've already taken a look at our own solar system, the planets and everything else that orbits the sun. Now we'll take a look at other star systems. Can we see planets around other stars? Are those star systems just like ours? Or how different are they? A generation ago, we had not discovered any planets orbiting other stars. So all of these discoveries are pretty recent in the past few decades. If you go to exoplanets.nasa.gov, you can see the updated numbers of confirmed exoplanets. An exoplanet is a planet orbiting some other star, not the Sun. They might also be called extrasolar planets. As of the day I'm recording, we've confirmed 4,306 exoplanets. 34% are Neptune-like. 31% are gas giants like Jupiter and Saturn. 31% are super-Earths, that is, of densities comparable to Earth but more massive. And about 4% are terrestrial, like Mars, Mercury, Venus, and Earth. So how do we discover these planets orbiting other stars? There are several different methods for discovering exoplanets, and we will just discuss the four most common. In the exoplanet census on the left, there's a plot of planet mass in the vertical axis by orbit period in the horizontal axis. These are both on logarithmic scales. To understand the context, we can find where Earth would be. Earth has a mass of 1 because this is being measured in Earth masses. So a mass of 1 and Earth's period is 365.2425 days. So 100, 200, 300, 400, a little bit in, going up from here. So Earth would be about right around here. So notice how most planets that have been discovered are higher up on the plot. That means they are more massive than the Earth. And it makes sense that we would discover the more massive planets first. So there is some observational bias there, and also that most planets are to the left of where Earth would be. And that's because they are on shorter orbits. They orbit their stars quicker than the Earth orbits the sun. And there's also an observational bias there. It's easier to discover the planets that are closer to their stars because they're more likely to transit their stars. Transit photometry is the most common method for discovering exoplanets. They're also more likely to perturb their star's motion, and that's by the radial velocity method. We'll be talking about that as well. But first, we'll talk about the more intuitive way for discovering exoplanets, and that's by direct imaging, taking pictures. HR 8799 was the first multi-planet system where the planets were discovered through direct imaging. This system includes 4 giant planets, most likely more massive than Jupiter, located 129 light years away, and they are all on wide orbits. That way they are far enough away from their star that we can observe them by direct imaging. But imaging only accounts for 1% of discovered exoplanets because stars are really, really far away, and only the largest planets far enough away from their stars can be seen directly. Most planets would be lost in the glare of their stars. The light from the stars completely overpowers the light from the planets. The radial velocity method, also known as Doppler spectroscopy, has discovered a lot more planets around other stars. Otto Struve first proposed this method in 1952, but at that time, technology was not ready. This method uses Newton's third law, that there's an action and reaction force. Notice in the bottom right that there is a planet orbiting a star, but due to the planet's gravitational pull, the star also pivots or wobbles on an orbit. we can detect light from that star and the spectral lines and how they are shifted toward the red or toward the blue, depending if the star is moving away from us or towards us. And if we see periodic shifts, then we know it is wobbling because of a planet's orbit, a planet pulling on that star. This provides information about the planet's mass, at least the component of the mass that is along the line of sight. Notice if we were observing a star and planet from above, like this depiction, we would not actually detect any radial velocity because the star would be moving to the left, right, up, and down, but not towards us or away from us. So we would not be able to discover that planet through the radial velocity method. But if that orbit were tilted edge on, then we would be able to discover it. Or if it's partially tilted, we would still be able to discover it, but we wouldn't really know its true mass that way. This method favors the discovery of high mass planets close to their stars. Jupiter, for example, causes the Sun to change velocity by 12.4 meters per second over Jupiter's period of approximately 12 years. The Earth causes the Sun to change velocity by 0.1 meters per second over 1 year. 0.1 meters per second is not as easy to detect. The first planet discovered through the radial velocity method is called 51 Pegasi b. It is orbiting the star 51 Pegasi, which is significant because it is a main sequence star, like our Sun. In 1995, 51 Pegasi b was discovered, and it is called a hot Jupiter because it is massive like Jupiter. It has a mass of 0.46 Jupiter masses and an orbital period of 4.23 days, very close to its star. Some limitations of the radial velocity method are that it can only measure motion along the line of sight. That's why it's called radial velocity. A planet's true mass will be greater than the measured mass. Also, stellar variability prevents planets from being discovered around variable stars. Another method for discovering exoplanets is transit photometry, the transit method. If from Earth we can see the planet's orbit edge on, then it will cross in front of its host star. When it does that, it blocks a little bit of the light from that star. We can measure the amount of light coming to us from that star, and we can notice periodic changes in that star's brightness. From the transit depth, which is how much light the planet blocks, from the transit duration, how long it blocks that light for, and from the ingress and egress duration, how long it takes the planet from blocking none of the star to go over that edge of the star and blocking all the light it can from the star, and then back again to blocking none of the star. From those values, we can determine the star's mass and radius, the planet's radius, the semi-major axis, eccentricity, and inclination of the planet. Limitations are that it only works for planets that transit, which is more common for planets that orbit very close to their host stars. There's also a high rate of false positives. For this reason, there's need for follow-up confirmation by other methods, such as the radial velocity method. If the radial velocity method confirms a planet discovered through transit photometry, then we know the mass and radius of the planet. So we can calculate its mean density and determine the type of planet it is. The first discoveries through transit photometry were in 1999 and 2002. In 1999, HD 209458b was found to be transiting, but that planet had already been discovered by the radial velocity method. At least we were able to prove that this method could detect exoplanets. In 2002 was the first exoplanet to be discovered through transit photometry, Ogle TR56b. Since then, there have been ground-based surveys such as KELT and HATNet, and space-based missions, starting with the French Corot mission, and then the Kepler Space Telescope, and now TESS, the Transiting Exoplanet Survey Satellite. The Kepler Space Telescope, launched in 2009, used a photometer to monitor the brightness of about 150,000 main sequence stars in a fixed field of view and detected 2,662 planets in 9.5 years of service before running out of fuel in 2018. Then TESS was launched in 2018. It has completed its 2-year primary mission and has identified about 2,000 planet candidates. It is continuing to search for exoplanets. Another method is called gravitational microlensing. By general relativity, we know that stars and other massive objects bend light. This is the explanation of what is called the Einstein ring. As you can see in the top left, there's a spiral galaxy behind an elliptical galaxy, but that elliptical galaxy in the foreground is bending the light from the spiral galaxy in the background, so we see the spiral galaxy all around, sort of in a horseshoe. It's not a complete ring here, but it's pretty close. As a result, we detect more light from the spiral galaxy than we would have if that elliptical galaxy were not in front of it. On a smaller scale, then, by this method, we can detect a one-time increase in a star's brightness due to lensing from chance alignment. And when there are planets orbiting the stars that are used as a lens, it makes a contribution to the light curve that we get. This is able to constrain the mass of the planet and its radial distance from the star. But the disadvantage of this method is it can't be repeated because it's a chance alignment. And these stars are usually too far away for follow-up observations by another method. Today, there are networks of robotic telescopes that have been performing observations to look for gravitational microlensing events. Are most star systems like our solar system? Not as many as we used to think. We'll talk about star spectral types next class, but only 6% of stars have the same spectral type as our Sun. We've found many systems with hot Jupiters, something we didn't expect to find. We've also found an abundance of mid-sized planets. The most abundant type of planet we've discovered in other star systems is in between the mass of Earth and the mass of Neptune. We don't have any examples of that in our solar system. So is it better to call them super Earths or mini Neptunes? We don't have a good understanding of this yet. The question on the search for life in the universe has to begin with the Fermi paradox. Enrico Fermi put it succinctly with the question, where is everybody? There's a lot to unpack in these 3 words. If the universe has been around for billions of years, isn't that plenty of time for intelligent extraterrestrial civilizations to traverse the galaxies? The universe's silence is called the Fermi paradox. We've only been recently watching and, so to speak, listening with telescopes. It was suggested to observe at a frequency of 1,420 megahertz, which corresponds to a wavelength of light of 21 centimeters, because hydrogen, the most common element in the universe, emits radiation at that frequency, which should be familiar to any technologically advanced civilization. At that frequency, a strong narrowband radio signal was received by the Ohio State University's Big Ear radio telescope in 1977. This is known as the WOW signal because the person who was reviewing the transmissions circled it and wrote WOW. The signal sequence lasted for the full 72-second window of observation, but it has not been detected since. We don't know exactly where it was transmitted from, but it remains the strongest candidate for an alien radio transmission ever detected. In 1974, a few years before the WOW signal, the Arecibo radio telescope in Puerto Rico had sent a message towards the globular cluster Messier 13, or M13, which is 25,000 light years away. So if there are aliens that receive this message in M13 and transmit something back, we won't receive it for approximately 50,000 years. This was meant more as a demonstration of human technological achievement, sort of like sending a car into space, rather than a real attempt to enter into conversation with aliens. The content of the message was designed by Frank Drake, who we'll talk about again soon, with help from Carl Sagan and others. On the left is a representation of the data that we transmitted. Colors have been added to separate the elements of this content. First are the numbers 1 through 10, then the atomic numbers of the elements that make up DNA, hydrogen, carbon, nitrogen, oxygen, and phosphorus, then the formulas for the chemical compounds that make up the nucleotides of DNA, then the estimated number of nucleotides in the human genome, and a graphic of the double helix structure of DNA. Then there's a graphic of a human being, the height of an average man, and the human population of Earth. Then a graphic of the solar system indicating which of the planets the message is coming from. And finally, a graphic of the Arecibo radio telescope and the diameter of the antenna dish. Of course, we wouldn't expect extraterrestrials to speak the same language as we do. So all of this data is represented symbolically. Hopefully, they would be able to decipher the symbols and understand what we are trying to say. It also isn't likely for there to be life in Messier 13. It's less likely for planets to be habitable in globular clusters due to the presence of so many nearby stars, which would perturb orbits of planets, so they would not be stable for long. We don't really know anything about the probability of extraterrestrial intelligence, but the most effective way to visualize the probability of extraterrestrial intelligence is the Drake equation. Frank Drake is the one who came up with this. We can estimate the number of intelligent extraterrestrial civilizations with communication technology if we multiply the mean rate of star formation in our galaxy by the fraction of stars that have planets, by the mean number of planets that could support life per star with planets, by the fraction of life-supporting planets that develop life, by the fraction of planets with life where life develops intelligence, by the fraction of intelligent civilizations that develop communication, by the mean length of time that civilizations can communicate. At the time that Frank Drake published this equation, none of these values were known, but we now have good estimates on at least the first two. Our star, the mean rate of star formation, is about 3 stars per year, and F sub p, the fraction of stars that have planets, is about 1. Pretty much all stars have planets. For the rest of these values, we have to make wild guesses. First, let's be optimistic. Let's say that n sub e, f sub l, f sub I, and f sub c are all 1. And let's say the mean length of time that civilizations can communicate could be 1,000,000 years. Then the result would be that there are 3 million civilizations today out of 10 billion sun-like stars in our galaxy. But then we can come back to the Fermi paradox. Where is everybody? We could also have a more pessimistic view. And we can say, sure, n sub e, the mean number of planets that could support life per star with planets, could be 1. But let's say that f sub l, the fraction of life-supporting planets that develop life, is 0.001, or 1 in 1,000. Let's say that f sub I The fraction of planets with life where life develops intelligent is 1 in 100, 0.01. Let's say that f sub c, the fraction of intelligent civilizations that develop communication, is 3 per 100, or 0.03. And let's say that L is still a million years. From those numbers, the result is that we would be alone in our galaxy. I took these numbers for the optimistic and pessimistic views from a talk by Jonathan Lunin, a Catholic planetary scientist. And then he asks the question, why might the pessimistic view actually be reasonable? It took 80% of Earth's habitable history for intelligent life to develop. And what if we on Earth are precocious? The Drake equation can also be modified for an estimate of the number of intelligent extraterrestrial civilizations in the entire universe, approximately 200 billion galaxies. Especially if the fraction of life-supporting planets that develop life and the fraction of planets with life where life develops intelligence are really small, then we could be alone in the universe. But these are small number statistics, so it's largely speculation. We only have one example of an intelligent civilization. We only have one example of the origin of living from non-living matter. But the exploration of potentially habitable worlds in our solar system could give us a better grasp on F sub L, fraction of life-supporting planets that develop life. So missions to Mars, Europa, Enceladus, Titan, and so forth should help us constrain that value. We also often talk about life as we know it. What if there's life out there that is not quite similar to ours? Our life on Earth is carbon-based, but could life be silicon-based instead, or have some other base? Exploration of Titan is a prime experiment for this, since Titan has the hydrological cycle with methane and ethane instead of with water. But anywhere in the universe, there would still be the same laws of physics. The scientific question of whether there exists life elsewhere in the universe also raises important theological questions. Although I'm skeptical about the existence of life elsewhere, I have to remain open to that possibility. Our faith shouldn't say prematurely that there isn't life anywhere else, because what if someday we do discover life somewhere else? God can do anything he wants, and his ways are not our ways.